Hello friends, warm welcome in this video, that is enzyme kinetics. Friends, we have defined enzyme as a biocatalyst which increase the rate of. It means that the study of enzyme practically depends on the rate of a reaction. So the branch of chemistry or biochemistry which is dealing with the measuring and studying the rate of reactions is termed as kinetics. So all the mathematical calculations which are concerns with the rate of reactions or measuring the rate of reactions are nothing but the kinetics of the reaction. In physics, the alternative term dynamics is used for the same. What we are studying in kinetics today, all these works is based on the laws of mass action, which was proposed by Cato Maximilian, Goldberg and Peter Weich in 1867. So what is this law of mass action? The law of mass action states that the rate of reaction is proportional to the product of the activities of each reactant, and each activity being raised to the power of the number of molecules of the reactant taking part. So this can be indicated by reaction equation: concentration of A plus concentration of B is the products. Thus the rate is proportional to the activity of A raised to power its concentration into activity of B raised to power its concentration. Friends, for practical purposes, the term activity is usually replaced by concentration. Although strictly speaking, it is only equal to the concentration in ideal gases and in very dilute solutions only. The study of law of mass action led to the concept of the order of reaction. The order of reaction is nothing but the power dependence of the rate on the concentration of each reactant. So these order are of various types. We will learn each of them. First, the first order reaction. First order reaction is one which proceeds at a rate proportional to the concentration of one reactant. Thus, for first order reaction of type A is converted into P. A is a reactant and P is a product taking place at a constant temperature and pressure in a dilute solution. Reaction rate V at any time T is given by V is equal to minus D concentration of A by dt is equal to plus D concentration of P by dt is equal to K concentration of A. Here we will see the meaning of each term. V is the rate of reaction, whereas V0 is the reaction rate at time t. K is nothing but the rate constant. Concentration of A is the concentration of reactant at a time t. Concentration of P is the concentration of product at time t. Minus dA by dt indicates the rate of decrease of concentration of A, whereas plus D concentration of P by dt indicate rate of increase of concentration of P. So this equation indicates the first order reaction kinetics. Then second order reaction. A second order reaction is one which proceeds at a rate proportional to the concentration of two reactants or to the second power of a single reactant. So for a second order reaction of type A plus B which gives product P, which is taking place at a constant temperature and pressure in a dilute solution, the equation will be V is equal to minus D concentration of A by dt is equal to minus D concentration of B by dt is equal to plus D concentration of P by dt is equal to K concentration of A plus concentration of B. Here also the terms having the same meaning as we have seen earlier. Similarly, for the second order reaction of a type 2A converted into product P, the equation will be V is equal to minus D concentration of A by dt is equal to plus D concentration of P by dt is equal to K concentration of A raised to power 2. A two reactant reaction can under certain circumstances be regarded as pseudo single reactant one. For instance, a reaction taking place in an aqueous medium and involving water and one other reactant are usually considered pseudo single reactant since water will be in vast excess and its concentration will not change significantly during the course of reaction. It should also note that zero order reaction is also possible. This is one whose rate is independent of concentration of any of the reactant. The term initial velocity V0 means the reaction rate at a time 0 and may be determined by drawing a tangent to the graph. The initial velocity depends on the initial concentration of the reactants. Ludwig Wilme in 1850 showed that the rate of acid hydrolysis of sucrose was proportional to the sucrose concentration at a constant acid concentration. All the term defined in the previous part. Therefore, we would say that this reaction was a first order reaction with respect to the sucrose. When the identical reaction but catalyzed by the enzyme invertase was similarly investigated, different results were obtained. Adrian Brown in 1902 showed that at a low sucrose concentration, the reaction was again first order with respect to the substrate, but at higher concentration it became zero order. This was found to be generally true for all single substrate enzyme catalyzed reactions. And for multi-substrate reaction, where the concentrations of all the substrates but one were kept constant. A graph of initial velocity V0 against initial substrate concentration S0 at a constant total enzyme concentration E0 was found to be a rectangular hyperbola as shown here. Such a graph has a general equation A concentration of pH0 by concentration of pH0 plus B, where A and B are constants. The constant A represents the maximum values of V0, which is often called as Vmax, and B is the value of concentration of S0, where V0 is equal to half Vmax. Although some enzymes do not give a hyperbolic graph, they often give the sigmoidal curve. The attainment of maximum initial velocity with increasing substrate concentration at a constant total enzyme concentration is a characteristic of all enzymes. The explanation for this feature was first given by Brown with a particular reference to the hydrolysis of sucrose, but subsequently found to be a general application. Enzyme and substrate combine to form an enzyme substrate complex which undergoes a further reaction to break down the enzyme and products. Thus, the equation E plus S converts into ES with a rate constant K1, which again converts into E plus P with the rate constant K2. The overall rate of reaction, that is the rate of formation of P, must be limited by the amount of enzyme available and by the rate of breakdown of enzyme substrate complex. If the substrate concentration is sufficiently high, it will saturate the enzyme, that is, force an immediate reaction with each available enzyme molecules to form a enzyme substrate complex. Under these conditions, therefore, there will be no free enzyme present and the concentration of enzyme substrate complex ES will be total enzyme concentration present E0, making the overall rate of reaction K2 E0 from the law of mass action. This is independent of a substrate concentration and so cannot be increased by using still higher substrate concentration. It is therefore maximum initial velocity possible at this enzyme concentration. Hence, Vmax is equal to K2 concentration of E0. In contrast, at a very low substrate concentration, the enzyme will be far from saturation and the overall rate of reaction will be limited by the rate at which enzyme substrate molecules react to form enzyme substrate complex. At a constant enzyme concentration, this will be proportional to the substrate concentration and therefore a first order reaction will result. At an intermediate substrate concentration, the enzyme will be partially saturated with substrate and the order of reaction will be somewhere between zero order and first order. Note that the term saturated and partially saturated refers to the population of the enzyme molecules and not each individual molecule. An enzyme molecule which binds a single substrate molecule cannot in itself be partially saturated at any given moment, but a population of such molecule can be some being substrate bound and some free. The existence of an enzyme substrate complex was first demonstrated experimentally in 1936 by spectroscopic studies on the enzyme peroxidase and catalase. Since then, the presence of such complexes has been amply documented by X-ray crystallography, ESR, NMR, fluorometry, and other various techniques. So the various equations in enzymology which are based on this basic phenomena we will study in next videos. Thank you.